Alright, so our next topic is light in the electromagnetic spectrum. Alright, so we already talked before about what an electromagnetic wave was, at least the idea that it doesn't have to move through any kind of medium. Here it gives you more information and tells you that it has an electric field traveling in one direction and a magnetic field traveling in a different direction. I'm going to take that back. Both in the same direction, but just different ways. One is longitudinally, remember that's a compressional wave, and one is transversely moving up and down. Okay, electromagnetic waves can travel through empty space, I just said that. They are electrons that change speed or direction. It gives you an example. Specifically, light is when an electron jumps from one position in the atom to another, and we call those photons. They can travel 300 meters per second through empty space. Of course, when they hit any other medium, they slow down. Let's see. It says, did you know that light travels from the sun, which is 150 million kilometers, to the Earth in just 8 minutes? Alright, the electromagnetic waves are arranged in order of wavelength and frequency. So the weakest waves, which have the biggest wavelength and the slowest frequency, are going to be at the beginning, and it's going to get faster and stronger as we move toward the end. So it begins with radio waves. Those waves are about the size of buildings. They're pretty big. They're produced when electrons move back and forth from antenna to antenna. This is a vocabulary word associated with radio waves. Modulation is the difference in amplitude or frequency. Where you know this from is the difference between AM and FM. AM is amplitude modulation and FM is frequency modulation. And then it gives you an example that the sound in TV is carried as the AM while the picture is FM, which is why sometimes you can see the picture and the sound are not going together. They do not travel together. And it can be interrupted by weather or mountains. We've come a long way since I was a child. Anytime it rained, TV was gone. Okay, microwaves are an example of radio waves. They are the strongest of the radio waves. They're used to cook foods, they're in cell phones, and also used for weather forecasting. Here's how they're used as weather forecasting. Radar waves is an example of microwaves. Radar stands for radio detecting and ranging. It's used to locate objects, track and predict storms. Infrared rays cannot be seen, but they can be felt as heat. 50% of the rays from the sun are infrared. And it says that all objects give off an infrared ray at some level. The hotter it is, you can see this color range over here. In this range right here, we have yellow and white as the hottest, and then your red and oranges are in the middle. And when it's cold, you have the purples and the pinks. Okay, so next on the spectrum is visible light. It's the only electromagnetic wave you can see. You should know the order of the colors of the rainbow. Roy G. Biv says that life could not exist without visible light, and you should be able to tell me why. UV rays are used to kill germs, to destroy bacteria, and to preserve food. They can be seen by insects. This is what we feel as a sunburn. So when we wear sunscreen, we are blocking the UV rays. The ozone layer thankfully absorbs most of it, but not all of it. Next on the spectrum are X-rays. It says that the bone absorbs the X-rays rather than letting it pass through, which is why we see bones. Stars give off X-rays as they explode. They are a potential health hazard. We talked about that when we learned about radioactivity. It can cause defects to the human cells. And then the last wave on the spectrum are the gamma rays. They have the most energy. You learned about this also in radioactivity. They're given off in nuclear reactions. So if something were to explode, some type of bomb, They cause radiation sickness, and they're deadly if you have excessive exposure. Okay, this is where you're going to stop for today. You should just make sure that you have every type of wave that exists on the electromagnetic spectrum written down from weakest to strongest, so you should end with gamma rays, and bring that in with you next class. Okay, so now we're going to talk just specifically about light. Luminous objects are anything that gives off its own light, like the sun is luminous, a light bulb is luminous. Illuminated means it's lit up by something else, so the moon is illuminated. It doesn't produce its own light. Instead, the light we see is from the sun shining on it. The three types of light. We have incandescent, which is light that creates heat. Light bulbs, not all light bulbs create heat though, but the older light bulbs. Candles. Fluorescent light is a cooler light, and you'll see in the lab that we do that you can tell it's much cooler. But it also uses less electricity, and more we're turning to fluorescent light. Neon lights use noble gases to produce that bright color. The most commonly known is neon. Okay, light is more a stream of photons than a wave of energy. And we're going to look at why. But because it has properties of both, scientists are not sure if it's wave-like or particle-like, so they just say that it's both. Okay, we're going to look at some laser lights and kind of prove that it's a stream of matter as well as energy. Okay, concave mirror versus convex mirror. A concave mirror caves inward. Okay, that's the best way to remember it. When you're right up to it, you can see right side up, but if you move away, it turns upside down. So look in a spoon on the caved in side of it, and you'll see that you look upside down. A convex mirror curves outward, and what you're seeing is smaller, but you can see a bigger area. So we would use this as a rear view mirror, maybe like the picture on the right in a store, so that you're able to watch your people in your store. Okay, without light, there are no colors. Think about it at night when all you have is a little bit of light, maybe from a street light or a moon in your room. Mostly you just see blacks, grays, and whites. You don't see colors. Okay, and this is because, remember the Roy G. Biv we said light has in it. When it hits something, what you see is what's not being absorbed. Okay, so if you see yellow, yellow is not being absorbed. Everything else is. Okay, and then 3 vocabulary words to know. Transparent means you can see through it. Glass, water, air, you can see right through. Translucent means it's kind of foggy. So light goes through shadows, but you don't really see exactly what's on the other side. So looking through wax paper or frosted glass. And opaque means you can't see through it at all. Okay, the last 2 words for this unit, nearsightedness versus farsightedness. So a nearsighted person can only see what's near. A farsighted person can only see far away. Farsightedness is more common among teenagers, but as you get older, take that back. Nearsightedness is more common, but as you get older, farsightedness becomes very common. It's usually around the age of 40 that you can't see far away anymore, or up close. All right, just bring all your notes in, and we're going to have another lab. See you guys in class.